last time you did an excellent exercise of summarizing what is oscillating inside Bohr atom, or what is the phase angle of the waves inside. So it is related to action. And now we need to borrow this idea and try to make it more general. So overall goal that probably we will complete, maybe not Friday, maybe Monday next week, will be equation for electrons as wave, and its named equation, Schrödinger equation, you might have heard it. But we want to derive or show that it is legitimate. And everything we do right now before Schrödinger equation is just preparatory steps so that we have right foundations. So if everything goes well, then today, then we should arrive to these equations, and I will be not surprised if you don't. So please let me know if any of these equations seem reasonable. Like first equation, just okay, completely wrong, more or less. Okay, so second equation. Anyone? Okay. Most down, or I saw someone in the middle. Okay, and then there is no reason to go further, to ask further, because everything is rest on this one. So, but the goal is to follow the chain of this equation, and the stuff right here will be our main tool for the whole semester, right? So we need to arrive at, and since it is so important, we are arriving with some delays, but with solid foundation. And I probably should introduce the equation to you and you the equation. Class of 2021, this is Schrödinger equation in the class of 2021. So you remember the wave equation has second derivative over space and second derivative over time, part of differential equations, and it deals with there should be the same symbol. So it is applied to something that oscillates as function of position in time. And in Schrödinger equation, you see instead of second derivative, there is a first derivative over time. And this Hamiltonian operator of total energy that we were briefly discussing before, it typically contains second derivative over space, plus some additional terms. But do not worry, we are not going to, I'm going to offer a lot of materials, but the main thing is here, and for main stuff we will approach slowly, and I'm confident that you will be you will have all details and understanding where it comes from and how to apply it. So everything I'm talking before this equation is just preparatory steps and some like logical and philosophical things. And I'll skip talking about this one before it will be time for it. So Euler equation is fine, right? It's like calculus 3, complex calculus, right? The wave function is something that is oscillating in Bohr atom and anywhere where electrons are flowing. And this equation that most of you turned down and some of you showed that more or less, it tightly relates to the verbal summary of the last lecture that you gave. So if we do have electron moving somewhere, for example, in the model of Bohr atom, planetary model, or it's just free electron, or anywhere in the molecule, as electron is moving, it accumulates action along the trajectory. right? And this action serves as a phase angle of oscillatory functions. We will see that sines and cosines are just not comfortable for oscillating electrons, for wave function of electrons. So when we use generalization of sines and cosines in form of this imaginary exponential, which is just summation of cosine and imaginary sine, right? And the S, which is action, we introduced last time. It depends on the trajectory. So the action that particle accumulates along the trajectory is entering the phase angle of this Euler exponential. And this is not a strict definition. This is not a strict proof, but it is kind of a little traffic sign showing where our thoughts should go. So if you accept this idea that this SPD maxima and minima in hydrogen, this oscillatory waves in Bohr atom corresponds to accumulation of action, we can hypothesize an idea that anywhere electron is moving, it accumulates action along its trajectory, and this action is placed as an argument of the imaginary exponential, and then it will be a wave function. And then we need to interpret it and speak about probability, where to find the electron. So how to get probability out of this wave function. So in philosophical sense, we are done with the course. This is the main idea. And the rest are, and we are not finishing the course now. The rest can be symbolically split on two things. First, how to implement this idea into equations that we can solve. Because right now, I'm not sure if it is easy to get action for complicated molecules. So maybe for hydrogen atom and free electron in free space one can do it, but in something complicated, it's a big headache. We need to find some appetizing equations that are possible to solve, at least by a computer. So it's part one. Part two is to check how would these equations apply to real world, select a couple of examples, a couple of models. Maybe by the end of this course, we will not be able to describe molecules like these crystals. We should focus on something simpler, but more or less realistic. And then we will compare predictions based on this philosophy and these equations with experiments and see if it makes sense, if it has some relation to nature. And then we will fulfill the goal of the course. We will at least interpret experiments in physical chemistry, right? And at most, we would be able to predict outcome of an experiment, like an instrument, or predict direction path based on knowledge of quantum theory. So this is a big goal that will be not 100% achieved, but at least we can pose it and we can have tools to achieve it when it is really needed. But in sense of the fundamentals and philosophy of the course, we are done. So if your little summaries that you wrote in your notebooks last week make sense to you, if you accept this action as a phase angle for imaginary exponential wave function, you have the main core of everything you need. Okay, so this equation is more philosophical, and I already started talking, and I will fail to go over all slides, but they will be repeating stuff that I'm chatting right now. Maybe if you just chat and focus on my equations, it will be easier than me distracting your attention by 40 slides, sliding quickly. So this equation was first offered by French aristocrat Prince Louis de Broglie about the same time as World War I, so slightly later. And he just told that, hey guys, all problems about chemistry, physics, and electrons can be resolved if we assume that electron is a wave and it just accumulates phase as it goes. And he got Nobel Prize just for this idea. He wasn't deriving any exact equations. So it's really valuable. Now, this equation is only an idea. It's not practical. If you want to make it a little really practical, we need to go to this one, but it is not, we are not yet ready. There is an intermediate step between the Broglie wave and Schrödinger equation. And this equation shows a very important thing. And just by pointing this equation and talking right now, maybe I'm running, putting the car in front of a horse. But it is also something that we will be doing during the course. So as we go through next week, we will get an interpretation of this wave function. And it is related to probability to find out from here and there, right? Now, there is a dream in maybe fairy tales and fantasy to have wizards who can change reality or predict the reality, right? This equation is implementation of this dream. So it is an equation for predicting future. So suppose we are a couple of weeks ahead, we all are masters of wave function and we know what it is, how to interpret it, and we know distribution of this function of two variables in all points of space at initial time. And then we can formulate a question of predicting future. What will be analogous wave function for the same system at the finite time, like after a certain time interval? So how to project past into the future. Make sense? And this yellow box is this prediction operator. It allows us to convert past into the future. If you would deal with only natural, material, big objects, and we will play Newton's equation of motion, we set initial conditions like position, velocity, solve Newton's equation, and predict where particle will be. But if it is something distributed that works as a wave, it will not work. Instead of this Newton equation, we have this yellow box. And let me attract your attention to the similarity between this de Broglie idea and this predictive equation. So here is exponential, here is exponential. Here is imaginary unit, there is imaginary unit. Here is Planck constant, there is Planck constant. And then energy times time. So Hamiltonian operator is energy. Energy times time has dimensions of action. So in some sense, this is a way how to compute something related to action and place it into the power of as a phase of the exponential. So it's a natural continuation of this idea with a little bit more specifics. So to be not as a general idea more specifics, it's not just exponential with phase. It is a conversion of the past to the future by accumulating some oscillations in this function associated with change of action. Whew. Okay, 22 minutes. Now, basically, we arrived to the end of today's lecture, and I will show some slides that I wrote a couple of years ago and see if the slides will help us to make our understanding of this idea stronger. But basically, if you agree with what is shown in this slide, you're already done. You have all things. I'll skip stuff. So it is my way to try to do this little writing from the previous lecture. So along the motion, we accumulate action, and it is used as a phase factor. So position and momentum, same dimension, and they can be used as if it is dimensionless, it can be used as an argument. Okay. So phase angle is action divided by Planck constant, because dimensions of Planck constant are the same as for action. So it's energy times time, joules times second, or whatever units you're using. And we are going to plug this phase angle into a trigonometric function, but instead of sines and cosines, we are going to use complex numbers. It is not the way to torture young minds. It was found that with exponential functions, everything is more natural, because differentiation and integration of exponential is the simplest calculus operation. So it reproduces the function itself, and the complex I is square root of -1, right? From quadratic equation, and complex number is real and imaginary thing. So we briefly chatted about it last Wednesday in the lab, right? So real and imaginary, phase angle and distance. And there are ways to convert like this x and y projections as distance times cosine, distance times sine, and one can find distance by the Pythagorean theorem, and this complex number is distance cosine plus I sine. So it's just a basic introduction of this complex numbers. So Euler equation, the first one you had in the summary, right? So it was a blind German mathematician who came here to Russia in about 1780s, because he was offered good position at the major institution. I'm going to skip this thing, but I cannot pass through. This was one of the little points of joy when I was like in the second or third years of undergraduate studies. So there is no time, but I cannot bypass it. Maybe some of you will be sympathetic to my feelings about this equations. When I was in the high school, I was so angry on my teachers and class material, because we were mandated to memorize equations of sine and cosine product and summation. I don't know if it was the same in your classes, but there is no logic. There are just 20 equations that you need to memorize. It irritates a lot, right? And this little thing, no one was personally teaching to me, but I suddenly realized that all these equations can be rederived in 3 minutes. And here is just a brief thing. It wasn't, one needs it in high school. When you are in college, it doesn't help anymore, but you still, I knew that we shouldn't memorize these equations. They all can be easily derived. So, you know the rules of products of exponentials. If there is a summation of 2 arguments, it can be represented as product of 2 exponentials. Make sense? Now, if you plug in Euler equation here, literally, and plug in Euler equations there. So here it will be cosine and sine of sum. Here will be cosine of first argument, cosine and sine of the second argument. And then you just pull everything on the left and right side. So you multiply these 2 things, and then establish equality between real part and imaginary part. And then you realize that like summation of this cosine of some I some sinusoidal of some will be product cosines real, product of sines real, and then product of sine and cosine imaginary. And you can say cosine real part here must be equal to real part here. So cosine of some is cosine alpha cosine beta minus sine alpha sine beta. Sine alpha plus beta, we make equality between imaginary parts, will be sine alpha cosine beta plus cosine alpha sine beta. So if your young years were tortured by trigonometry, now you can feel that you're a winner and you don't need to wipe off all these members and just rederive it and do when it is needed. Make sense? I don't know if it brings you much joy, but maybe for some of you it does. Okay. Goal is to predict future. I agree. Just a little thing. Star means flip the sign in front of imaginary unit. Is it okay, or you hear it for the first time? Star is flipping sign in front of imaginary unit. Don't hesitate to show if you never. So it's just a definition. If you apply the star means the formal name is complex conjugation. And if we have a complex number in this plane, with imaginary, star means you just make mirror reflection. And mathematically, you just flip the sign in front of imaginary unit. So if you represent it in projections, you put minus in front of imaginary star. If you use Euler equation, you can just put minus 0. And then exponential, imaginary exponential with star times imaginary exponential without star will be always 1. And one can prove it. One can prove it in the following way. This Euler imaginary exponential means you take the length and you rotate it by the angle phi. And here, second time, you rotate it by the angle minus phi, means you return it back. So if here is our vector of the length 1, first we move it to plus phi, and then move it back by minus phi. And we get always 1. So it is an interesting observation telling that if we have complex function and multiply it with and without conjugation, we will get a real number. So sometimes it will be not 1, but it will be a real number. And it is one of the procedures that you get, and all our observables in nature, in experiments with instruments are real numbers. We do not observe, we do not touch complex numbers, right? So it is one of the prompts how to get something observable from the wave function. And it brings us close to interpretation of the wave function. If you already found it by philosophy, by calculations, by mathematical equations, and then we need to convert wave function into probability to find electron here and there, we need to take complex conjugation of the function, multiply it by itself, and then it will distribution. So this SPD orbitals that we draw, they are typically drawn as probability density, and they are real. Sometimes people in computational chemistry do not do this conjugation and take only the real part of the wave functions and then plot positive and negative. And there are nice orbitals which are like green and red. Bubbles. Bubbles, yes. But it is a little safer philosophically just to take absolute value square or this conjugated times non-conjugated and make it always positive. Then it can be interpreted as probability density to find out from somewhere. 33 minutes. So it is basically what I just told. If you know the wave function, we take conjugation, we multiply it by wave function without conjugation, we will get the probability distribution. So it is probability to find electron in the space from x to delta x and at time t. And if you want to find probability in the certain range, we need to integrate. If you integrate from minus to plus infinity for the whole range of definition, we should get one. We are speaking about one electron. So this probability for the wave function should be normalized. Means integral of the stuff should be equal to 1. Is it okay? Or needs more? Okay, good. So this is something that comes to actual physical chemistry and quantum mechanics. We are slowly moving from philosophy to practical aspects. It's how to interpret wave function. So I do have a logical flow in my lectures, and if you find, I don't hope that you have time to find it, but there is a thing that I cannot learn myself through the years. And if you come with a bright idea, I'll gratefully accept it. And you will see it on a couple of slides. So the action is defined as integral of Lagrangian along the trajectory. And then it would be very natural to take this accumulation of fringes of oscillations as a way to go from the past and 0 to the future. Time is bigger than 0. So just action that would connect point x and point x prime in these wave functions. By now, I didn't lie. Everything is logically clear. But by some reason that is not clear for me, it is accepted in the quantum theory to instead of Lagrangian, one integrates Hamiltonian. So it just flips the sign in front of potential energy, which looks a little crazy to me. But there should be theorems unknown to me that can probably justify it. Right now, let's just accept it because this approach predicts behavior of natural objects very reasonably. But I'm open to learn this little problem. Okay, so we can consider action as integral of Lagrangian over time. Or if time interval is really short, infinitesimal delta t, its integral can be replaced as a product. Lagrangian at this time times increment of time. And if you do this crazy replacement of Lagrangian to Hamiltonian, you have Hamiltonian total energy at time t multiplied by delta t. So this product should be serving in place of action as a phase angle of this oscillatory stuff. So if you propagate, means project forward from past to the future, our future prediction in a very short time, it will be total energy times increment of time, right? Now, if the increment of time is longer than infinitesimal, if you cannot use just replacing integral by product, we should do actual integration. So we take total energy operator of the system at time t, and then just integrate it from initial to final time. And then this will be yellow box that projects us from the past, from initial time to the future. Any objections? Or like, are you okay with this equation? You opposed, or you need more discussion, explanation? Okay, yeah, thank you for accepting it. It was the least supported step, and I'm exaggerating, but basically for the just action in the like wave of electron with this phase factor, it was a Nobel Prize in physics by Prince Louis de Broglie. For equations like this, like converting it into this form of propagation, not only for this, but partially, it was Nobel Prize for Richard Feynman, who you may have also heard that name. So all the world use Schrödinger equation that we are going to learn in shortly, and he declined to use a Schrödinger equation for some problems and used only this way of predicting the function. And it was very helpful in speaking about like nuclear physics and the design of like reactors and bombs and stuff like that. And this yellow box can be called as evolution operator, while the T is called time ordering, which means in this integral we always go from past to the future. Mathematically, one can go back from the future to the past and tell no, it's just each time step after each other, just in case if someone objects. Okay. Now, I think we are doing good. We went over most part. Let me check if we have better. Yeah, I'll go through the ugly slides, but there is something nicely typed later. So, and I'll better tell by words and then illustrate by some writings. By now, I understand very much that if you make a quiz or exam with closed books, it will likely most of us will not reproduce these equations. But for superficial, basic understanding of concepts, I see in your eyes that you are on the same page. And if needed, you can just take copies of this materials and do something. So by now, you did agree that you can predict the future, or we can project wave function from past to the future by a small interval of time, even non-small. But now let's imagine a mathematical experiment. Suppose we want to predict future twice. So we have same like train with several stations. We project from the past to the present, let's say, and then we project from present to the future. If you want to report actual future, we can mathematically represent these two time machines for moving forward in time as applying this evolution operator twice. First, from the past to the present, and second, from present to the future. And it will be just product of two evolution operators, right? Two imaginary exponentials, which will differ just by limits of integration. Or if we are talking about recent past and very soon future, instead of integrals, we can have this just delta t time intervals multiplied by the total energy operator. So delta t energy operator in time 0, delta t operator energy in time 1, right? So two evolution operators. And if we want to combine product of two exponentials, we just add together powers, the phase factors of these two exponentials together. So it will be one exponential with summation of this energy times delta t, energy times delta t. So it's kind of trivial, right? So we can chop the evolution to the product of several infinitesimal evolution operators. So at each point of time, we can make a little time evolution. And I think it is the same idea, just with little better typing. So if you chop our timeline onto intervals, delta t first, second, and so forth, the evolution forward in time can be initial wave function, then evolution during delta t, then evolution delta t2, and so forth. So by this first infinitesimal evolution, we go from time 0 to time 1, right? And then we apply second infinitesimal evolution, we go from time 1 to time 2. And then we have the timeline going from the past to the future. Make sense? Okay. 44 minutes. And this summation of arguments is nothing but integral, right? So U is typical letter for this evolution operator, and it is what we put in the yellow box. Really? Nothing else? Well, I haven't expected myself to be so quick. I thought when I was starting this course, I was asking students to stay half an hour after, and you were saying maybe we still will leave sooner, but maybe try to. Oh, I skipped Schrodinger equation, but it will be too much. Basically, just look into the Friday meeting. If we apply time derivative to the evolution operator, we will derive Schrodinger equation. But and then it will be used for the rest. But let's maybe try to write one sentence in your notes right now about the evolution operator. Like what is evolution operator, how it is related to action. Just briefly, one sentence. So it doesn't need to be really, yeah, just about past, future. Just try something like what you can memorize. Trying to get something. Not yet.
I have to say this might be your slide.
Yeah, maybe if you find, I'm not sure if it was typing in more, but maybe there are some words. Just a bit for sure. Just a bit for sure. So Joshua and May and Alison, also please try typing or writing. I apologize if I will not ask you, but maybe it's important for you as well. Sorry, the camera is not able to catch all of you if you want to be famous, but let's try. So Adam, can you try just summarize?
Oh, I just said the evolution operator is used to describe the degree and manner a wave function changes between initial and final time.
Okay, yeah, thank you. Sibyl?
Okay, so basically I wrote that since we already previously had determined that electrons accumulate action along trajectory, so using the basically the evolution operator allows us to predict using the past where the electron will be positioned at a certain at a location at a certain time in the future. So basically that's what.
Okay, yeah, thank you. Right.
Said evolution operator acts like an integral and acts to predict the future multiple times in a row by adding multiple phases together.
Okay, yeah, great. I learned more by listening to you guys. Lola?
Evolution operator explains the change in wave function by explaining time altering in a short interval. Since the goal is to predict the future, it's also a function of Hamiltonian action.
Okay, yeah, thank you, thank you.
I said the evolutionary operator can be used to predict the position of an electron in the future from the past.
Okay, yeah, excellent. It's but it goes to the core.
I basically says something along the lines of the evolution operator gives a description of the phase of a wave over different time intervals to predict the future.
Okay, yeah, thank you much. So Josh, May, and Alison, I think we are already over time, but you can send your little paragraphs to me if you would like. So we are already 1 minute over time. I would like to announce where's the camera. Meeting is done. Everyone is welcome to disconnect, and we will slowly continue labs tonight, and they will be projected through Zoom. So if you can come to the 1:32 at 5. If you cannot, try to log in, and if you have a scheduled contact, I will record and share. Okay, see you tonight and on Friday. Sorry for keeping you a little longer.